One of the first questions we address for our customers in a potting application is how to implement the use of the potting compound. We help the customer address common questions like, will this flow properly in my part? How long will the material flow? How long before we can move the potted units? And how can we speed up our process? All these questions can be answered using a rheometer. First, what is a rheometer? A rheometer is an instrument that simultaneously measures both the flow and deformation of materials. During the curing process of a thermoset, these fluid and elastic properties are dynamic, making a rheometer key to the characterization of the curing polymer. More specifically, we look to analyze two main properties as the thermoset cures: the storage modulus and loss modulus. The loss modulus is the measure of the fluid properties of the material, versus the storage modulus is the measure of the polymer or elastic properties of the material. In this graph, you see the quantitative analysis of the loss and storage modulus of a curing thermoset. As the two-component thermoset begins to react, you can see that both the loss and storage modulus increase. They will both continue to increase until they reach what we call the crossover point. At this point, the elastic properties overtake the fluid properties, and we relate this to the no flow point in the reaction. This quantitative data is important because it shows three key pieces of information. 1. Optimum flow time of the thermoset. 2. Peak storage modulus build. 3. The crossover or no flow point. Each of these properties answers one of those important questions. Will this flow properly in my part? How long will this take to flow? How long before we can move our potted units? The portion of the graph that answers these questions are as follows. First, understanding where the lowest point of the loss modulus occurs tells us the optimum time you have to dispense the potting compound into your part. For the potting compound in this graph, we define this as where the material has a storage modulus of less than 10 to the negative 5 megapascals. For this graph, it is the beginning portion of the graph up to 4 minutes. The next question, how long will the material flow, can be answered by taking the first derivative of the storage modulus. The first derivative tells us the rate of increase of the polymerization reaction. The peak of this graph is the fastest rate of polymerization and thus fastest rate reduction of flow, indicating the point where the flow of the potting compound becomes increasingly restricted. Lastly, the crossover point answers the question, when can we move our part? At this point, the elastic properties overtake the fluid properties, and we relate this to the no flow point in the reaction, which is the crossover point. Now, the question you have all been waiting for: how can we speed up our process? The rheometer also has the ability to model all of the above data at elevated temperature. This graph shows the same thermoset cured at 4 different temperatures. As you can see in the graph, higher temperatures yield shorter time to the crossover point. This table summarizes the time for each temperature to attain optimum flow, first derivative peak, and crossover time. As you increase the temperature to speed up your process, you also shorten your flow and process time to no flow. The rheometer is a vital tool to model the processing of your potting compound. The ability to preempt the questions regarding, will this flow properly in my part? How long will the material flow? And how long before we can move the potted units accelerates your process engineering and time to market. The added benefits of modeling your potting process utilizing an elevated temperature can drastically reduce cycle time, increase throughput, and reduce manufacturing space for a net result of lower production costs.